Hi, everybody. Today I'm going to talk to you guys about temperature, which is a topic that I think most adults would say they understand pretty well. But in reality, if you ask them what does that mean when you say something has a certain temperature, they probably could not, unless they're a chemist or a physicist, they probably couldn't really tell you what that really means if you dig down far enough. But that's our goal today, is to try to dig down a little bit and see, when you say temperature, what is it that you actually mean? And so I'm going to start with something that you are familiar with in physics, and that's friction. So you have two surfaces. One surface is sliding across the other. This black surface on the top there is sliding across the other supporting surface. And what you can see here is that if you zoom in close enough, even though those surfaces may feel pretty smooth to begin with, they actually are filled with these bumps and these valleys. And the bumps and valleys are part of what causes friction. And what you can see is that they will hook on each other or collide with each other, and that collision does take away some of the motion. So we're going to focus in on just two particles here. So instead of looking at this whole surface and that whole surface, I'm going to look at just this black particle right there and that green particle right there, and keeping in mind that the black object is moving this way across the top of the green surface. So what's going to happen is this black particle right there is probably vibrating a little bit because all matter vibrates a little bit, which we'll talk about more later on. Maybe it rotates depending on what kind of material it is, but primarily it has this motion, this translational motion, and so it's moving from one place to another. Whereas this green particle right there, the surface is not moving with respect to us, so we don't say it has much translational motion, but that green particle definitely has some vibrational motion, probably, maybe some rotation, but primarily some vibrational motion. So this green particle is hanging out, just vibrating back and forth, waiting for something to happen, and along comes this black particle right there and collides with it. And when it collides with it, we have the same kind of collisions that we've been talking about in our past unit on momentum. So this black particle applies an impulse to the green particle, and the green particle applies an impulse back to the black. And so their motions change, probably their vibrations change, things like that. But primarily, because they've changed their motion, they've changed their kinetic energy. So kinetic energy is based, remember, not just on the mass, but also on the speed. And so the speed in this case would be the speed of vibration, right? So it's how fast it's moving as it's vibrating back and forth, as well as how fast it's moving in a translational way. From one place to another is what I mean by that. So kinetic energy changes because of this collision, and as a result, we end up with a transference of energy. That's what we're going to talk about. Okay, so if we're talking about particles, they can move in three ways. So they can have three different kinds of kinetic energy, really. The first way is translation, as I talked about before, so moving from one place to another. The second way is vibration, so oscillating back and forth around a midpoint, based off of, maybe if it's a solid, then the particle is in a matrix, and the matrix is trying to keep it in the same position, but it's vibrating back and forth, kind of like a pendulum or a spring pendulum like we used in class. You can see if it's given a little bit of sideways motion, then it's going to oscillate back and forth around that center position. And then finally, rotation. And rotation typically happens in a fluid, not in a solid. So particles can rotate around a particular axis, internal axis, but that typically doesn't happen in a solid, but definitely in fluids. And so you can have, particles can have any one of these three kinds of motion, which means they can have kinetic energy in a bunch of different ways. Now these particles can change their motion in a lot of different ways, or in at least a couple of different ways. And so we have listed here just two of them. The first one is when you have a particle that's in translational motion, or could be in vibrational motion if they're right next to each other typically, and then it collides with the particle that's near it or next to it. So you can see when this particle moves and hits the green one like two billiard balls on a pool table, the black applies an impulse to the green, and the green applies that impulse back to the black, and so they exchange momenta as a result of that collision. And that same thing happens if instead of translational motion, so if they're vibrating back and forth. You can imagine standing in a big crowd where everybody's really close together and just starting to move back and forth and see what happens. Sooner or later, the people around you are either going to spread out or they're going to start to move in sync with you. And so that's That's one option. Another option is that you could shine light onto a particular surface, and if it's the right kind of light, the right energy of light, it can get absorbed by the particles and then cause them to vibrate in a different way, or vibrate more, really, is what we're looking for. So, for example, you put food in a microwave oven. Microwaves are chosen specifically for that purpose because they do this to water molecules. So photons, or parts of light, waves of light that are in the microwave range, can be absorbed by water molecules in just the right way so that it causes them to vibrate faster. And that's why we use it to heat things up, which is what we're going to talk about in a minute. So here's just a quick reminder that kinetic energy is based off of both the mass and the speed of the object. In this case, we're talking about particles. It could be translational or rotational or vibrational motion, doesn't really matter. We can still take the mass of the particle that we're talking about and multiply it by the speed squared and multiply that by 1/2 to figure out what the kinetic energy is of that particle. Now, we can do something cool with the average kinetic energy of the particles, which we're going to do in just a second. But I want you to think about this for a second. The more energy I add into a system, like a substance, like, for example, I take a pot of water and I put it over a burner on my stove. What do you think is going to happen when that radiant energy, maybe chemical energy, is absorbed into that water? So the water is going to do what? Well, it's going to heat up. Its temperature is going to increase. Now, think about what we just said. We just said that as particles absorb that energy, they change their kinetic energy. They begin to translate or vibrate or rotate much faster. And on the other hand, on the big scale, we said when you add in energy, the temperature goes up. So again, we have particles moving faster, and we have the temperature of the substance going up. And so it turns out that those two things are exactly the same thing. So temperature is actually a measure of the average kinetic energy of the particles in a substance. Okay, so let's say we take two substances in containers, and we're going to say that the walls are very thin in the containers, so we don't have to worry about their own conductive properties. But we take two containers full of gas, and we put them next to each other. And it just so happens that on this side we have very small particles of gas, like like helium atoms, right? So helium doesn't like to work, doesn't like to combine with other things, so it's going to be just a single helium atom, and it's very small, right? So we say have helium on this side, and then let's say we have one of its bigger cousins, like krypton or something like that. So we put them next to each other, and so this mass for the helium atoms is very, very, very small. This mass for the let's use argon. How about so? This mass for the argon atoms is actually much bigger, and what we find is if we put them next to each other, after a little while, they're going to end up having the same temperature because the temperatures will equalize. So what that means, though, is, as we said just a minute ago, that the temperature is really a measure of the average kinetic energy of the particles. Well, kinetic energy is 1/2 mass times velocity squared. So the kinetic energy of the helium atoms is going to be, on average, is going to be the same as the kinetic energy on average of these argon atoms. But we know that the mass of the helium atom is much smaller and the mass of the argon is much larger. And so as a result, on average, these helium atoms are going to be moving much, much faster than these argon atoms, because we still have to say that the average kinetic energy for this substance and the average kinetic energy for this substance is the same. And so if we plug that in, we set these two equal to each other, we have a low mass, we should find that we must have a high velocity for these on average. And if we have a high mass, we must have a lower velocity on average for these. Okay, so now that we know what temperature is, it's the average. It's a measure of the average kinetic energy of the particles that are in a substance, whether that's translational kinetic energy, vibrational kinetic energy, rotational kinetic energy, some combination of those three. We need to be able to measure it, and we measure temperature in one of three ways, actually, in science. In the United States here, we could use the Fahrenheit scale. Sometimes they use it in the United Kingdom as well. So Fahrenheit was a scientist, and he put forth this scale that he based off of the coldest temperature that he could get a liquid salt water mixture to get, so he tried to cool it down as much as he possibly could in his lab. It was a really salty water mixture, and the coolest he could get it before it started to freeze was 0 degrees on his scale. And then the story goes, that I heard at least, is that he stuck the temperature scale, the new thermometer that he had built, into his armpit to measure the human body temperature, and he made that 100 degrees. It turns out that nowadays it's more like 97 or 98 degrees is actually human body temperature. So he's a little off, or we reconfigured things just a little bit afterwards. That's okay. I just always laugh when I see that. In physics, though, we're going to use one of 2 other systems, and they're based off of a little bit better, more standard measurements, and that's the Celsius system, or then the Kelvin system, which is closely related. So for Celsius, for 0 degrees Celsius, you probably know that at standard temperature and pressure, standard pressure, the pure water will freeze at 0 degrees Celsius, and at standard pressure, pure water will boil at 100 degrees Celsius. So that makes it a little bit easier to try to configure. If you needed to make a thermometer on your own, you probably could. So there is one other system, and typically we use that other system a little bit more often, and it's based off of the Celsius system, and that's the Kelvin system. And so the Kelvin system is the same size units. So the 1 degree Celsius measurements that you find between 0 and 100, we just convert into Kelvin, but we reset where 0 is. Okay, and the last piece is this, the Kelvin scale. So Kelvin is based off of Celsius. It is changed just a little bit because it takes into account the idea that there's this average kinetic energy. And as the temperature goes up, the average kinetic energy goes up as well. But think about it the other way. As the temperature goes down, the average kinetic energy goes down. So theoretically, there is a point at which you could take all of the kinetic energy out of a system, and then that would be the coldest possible temperature you could have. We call that absolute 0. And so sometimes the Kelvin scale is also called the absolute scale because it's based off of absolute 0. So 0 Kelvin, notice it's not 0 degrees Kelvin, it's just 0 kelvins, is defined as the coldest theoretical temperature. Theoretical because you can't actually get there. You could try to cool things down as much as you possibly could, but you can't, at least theoretically, you can't actually get there. That makes, because the 1 Kelvin is equal to 1 degree Celsius, that makes the temperature for pure water freezing at 273 kelvins, and then the temperature for pure water boiling at 373 kelvins. Now, kelvins are convenient because they're based off of a measurement that is based in good physics. Number 2, they are cold temperatures, right? So if you're dealing with astronomy, like I like to do, typically temperatures tend to be colder. Number 3, there's no negative numbers, right? So we have many days here in Wisconsin where we could be in the negative scale in Celsius, but you can't have that in Kelvin, at least theoretically, of course. And then from there, you can compare. It's a little bit easier to compare all sorts of objects throughout the entire universe once you have a system that doesn't really have negative numbers. So I don't know. I think it's a better system, and it's the one that we use in here. You probably used it in some of your ideal gas laws, maybe in chemistry class. So it's probably something you're familiar with.